Modern digital infrastructure generates terabytes of raw information every single second. To make sense of this massive volume, the tech industry relies on a chaotic, overlapping vocabulary of data science terms. Three specific disciplines dominate this landscape: statistics, machine learning, and data mining. Professional discourse frequently treats these terms as interchangeable synonyms. This confusion stems from shared mathematical foundations. All three fields employ the same core learning paradigms, such as supervised classification to categorize data and unsupervised clustering to group it. However, applying the exact same classification algorithm under the rules of each discipline produces three radically different software architectures. The divergence emerges through the specific operational constraints these systems are engineered to survive. Every data methodology is defined by its optimization target, the single metric the system values above all others. Statistics targets mathematical rigor. Machine learning targets predictive accuracy. Data mining targets algorithmic scalability. To understand modern data tools, we must analyze the specific metric the system is engineered to maximize. Statistics provides the foundational framework for modeling data behavior through random variables and probability distributions. Its primary role within data systems involves summarizing information, identifying noise, and managing missing values. This distribution curve shows a hypothesis test. Statistics uses this mechanism to verify that a discovered pattern is mathematically significant rather than a random anomaly. The optimization target here is absolute mathematical rigor and certainty. Achieving this level of certainty requires mathematically intense operations. This intensity leads to the primary limitation of traditional statistical methods: high computational complexity. This graph illustrates how computation time scales. As data variables increase linearly along the x-axis, the processing time on the y-axis explodes exponentially. When exposed to modern datasets distributed across multiple servers, these traditional methods hit a computational bottleneck and stop. A mathematically perfect model holds no value if a supercomputer requires 3 years to calculate the result. While statistics provides the bedrock of certainty, its computational cost creates an operational bottleneck for massive data. Machine learning focuses on systems that automatically learn from data to recognize complex patterns. These systems are designed to make intelligent decisions without being explicitly programmed with fixed rules. The core functions of machine learning, such as supervised classification, overlap with the primary goals of data mining. As this scatter plot shows, machine learning research prioritizes the ultimate accuracy of the predictive model above all other metrics. Research typically occurs within controlled environments using finite, manageable datasets. Scientists dedicate massive compute power to tweak an algorithm, iterating over the same data until the boundary line captures every anomaly, pushing the accuracy from 98 to 99%. Securing that final 1% of accuracy often requires an exponential increase in time and resources. This obsession with precision creates friction when moving models from a laboratory into a high-speed production environment. Machine learning solves automated pattern recognition, but the traditional focus on accuracy on static datasets can result in algorithms too slow for real-world deployment. Data mining functions as a highly application-driven engineering discipline. Its optimization target is algorithmic efficiency and the scalability of the system when applied to massive datasets. This dashboard highlights the data miner's priority. They will sacrifice a fraction of predictive accuracy to ensure the algorithm processes millions of records in milliseconds without exhausting memory. The engineering mandate is to maintain stability regardless of the data payload size. Data mining also addresses the structural complexity of modern data. Systems must accommodate massive network graphs, unstructured text, and high-resolution multimedia. The final constraint is temporal pressure from continuously arriving real-time data streams. These streams break traditional models that require data to remain static during analysis. Data mining is the art of survival, engineering theoretical pattern recognition to scale within the physics of continuous data ingestion. Data mining acts as the practical confluence of statistics and machine learning. A modern system uses this concentric architecture. The outer shell is data mining, engineered for scalable ingestion. Inside sits the machine learning engine, executing pattern recognition. At the center is statistics. Raw data enters, is processed, validated, and emerges as a golden nugget of knowledge. This synthesis allows tech companies to extract knowledge from massive repositories without their servers catching fire. Modern data science depends on engineering a precise operational balance between mathematical rigor, predictive accuracy, and absolute scale.